Next, we'll be introducing the sum and difference identities. These identities allow us to take a sine, cosine, or tan function where we have a sum or difference of two angles, and it gives us an equivalent where we can use individual sine, cosine ratios for each angle in order to evaluate. There's a couple of different ways we can apply these, but mainly our focus will be using these to make it a little bit easier to calculate an exact value. We won't really worry about deriving these, however, you can look in your workbook to see where they come from. We're just going to look at how we can use these to be a little bit efficient. You'll notice we have a couple of different symbols for our angle. We're going to be using alpha and beta. The idea is that we're just using two different variables since most of the time we'll have two different angles. One nice use of this is if you see something in a format like this, we have sine pi over 3 cosine pi over 6 plus cosine pi over 3 sine pi over 6. It sort of looks like it is formatted like one of the identities above. Which one would it match? Try and decide based off of the options there. Notice we have sine, cosine, and then cosine, sine. So that looks like a sine identity. In this case, it is going to be this one up here, sine alpha plus beta. We match that same format. So we can think of this as matching sine alpha plus beta. And this allows us to rewrite an equivalent statement. Let's zoom in a little there. So instead of having to write out 4 trig ratios, we can say this is equivalent to sine of alpha plus beta. Our alpha angle is pi over 3. Our beta angle is pi over 6. And the nice thing about this, particularly with this one, is we can add the angles really easily and get a nice, fast, exact value. So let's just do a quick common denominator. This will be 2 pi over 6 plus pi over 6. Together, that is sine of 3 pi over 6. And if you reduce that in the same step, we could tell this is actually sine pi over 2. And this is a lot faster to evaluate because if we look at the angle pi over 2 and find a coordinate on the positive y-axis, our y value is 1. So this is actually just going to be equal to 1. You could calculate this the long way because we do know exact values for the angle pi over 3 and pi over 6. But if you came back to this original, it's going to take you a little bit longer to do that compared to just combining them and only having to find one. More often, where this may be helpful is if we run into an angle where we don't actually have a special triangle for it and it's not one of our special angles that we're familiar with. So for example, if we look at this example, we want to find the exact value for cosine 345. But if we think about 345, it has a reference angle of 15 degrees. We don't actually know anything for a reference angle of 15 degrees. So this is a case where we would actually want to find two other angles that either add or subtract to 345 degrees. So we're looking for something in the format cosine alpha plus or minus beta. So can we find a pair of angles that either add to 345 or subtract to 345 where we do know how to find exact value for those angles? Noticing 300 would work really well, so would 45. So in this case, why don't we say cosine 45 degrees plus 300 degrees. So this is still cosine 345, but we're breaking the 345 into two convenient angles. Once we do that, we can now use our identity and break this into a longer statement. So this longer statement would be cosine 45 degrees, cosine 300 degrees, minus sine 45 degrees, sine 300 degrees. And if you're wondering where this came from, come back to our original identities and look at the addition identity for cosine. It's the cosine of both angles minus the sine of both angles. That's essentially what we're using. But this now gives us a way. We do have to calculate all 4, but hopefully that's not too bad. I'm going to come to the side and just do a little drawing for each angle. So 45 degrees, and let's just sketch a little triangle in there. That would be 1, 1, root 2. We can do something similar for the 300, so we may as well just draw that at the same time. 300 degrees is going to be quadrant 4. So that's a reference angle of 60. So then this will be root 3, but negative. This will be 1, this will be 2. That now allows us to find sine, cosine, or tangent if we needed it to for both angles. And then we can just fill in. So for example, cosine 45, look at your first diagram, decide what that is. I'm going to leave it unrationalized for now, and we'll rationalize afterwards. So 1 over root 2 times, for 300 degrees, cosine is also going to be positive, and this one will be 1 over 2. And then minus our sine ratios, sine 45 degrees, 1 over root 2. And then sine 300 degrees, which will be negative root 3 over 2. Okay, multiplying each term, we have 1 over 2 root 2. Minus negative, so why don't we write that as a plus sign, root 3 over 2 root 2. This one actually works out really nicely because we also have a common denominator. So we can say this is 1 plus root 3 all over 2 root 2. This is an exact value. This is probably where I would want to rationalize the denominator. So why don't we multiply it by root 2 over root 2, and I'll try and slide it in on the right here. We'll have root 2 plus root 6 over our root 2 times root 2 will become 2, so 4 in the denominator. So this is our simplified exact value, so no calculator needed, starting with an angle 345 degrees where we really didn't have a way to find an exact value, but breaking it into 2 nicer angles allows us to do that with the help of the identity. All right, let's look at the next one. For example 3, it asks us to do a couple of different things. The first thing is we want to try and express it as a single function. That's a really good hint that you're going to want to be using an identity to combine. So for example, cosine alpha plus or minus beta. You'll notice that we have some things being squared here, but you can just think about it as both alpha and beta are pi over 4. Pi over 4, also pi over 4. So if we wanted to rewrite this to make that a little bit clearer, you could think of it as cosine pi over 4 times cosine pi over 4, because that's essentially what cosine squared pi over 4 is. And then minus sine pi over 4 sine pi over 4. And if we match that to an identity, we can see that is the additive identity for cosine. So that's going to be cosine pi over 4 plus pi over 4. That is a single function. Although we could also combine the angles for a single function and say that this is cosine pi over 2. So applying the identity allows us to express as a single function, and then evaluating is pretty straightforward. We find pi over 2, the coordinate there is 0, 1, so our cosine is just equal to 0. Let's also take a look at one example that uses tangent, just because the identities look a little different with that. And it does look a little intimidating, but the key here is to kind of notice the pattern and notice that you can match it to one of the identities. So for example, we have 2 different angles, pi and pi over 3, but notice how we have the pattern of tan pi minus tan pi over 3 over 1 plus tan pi times tan pi over 3, and come back to your identities and match it. So if you can match it, that makes it a little bit easier to see it's going to be tan alpha minus beta, and we can rewrite as a single function right away. So this will be tan, our alpha is pi, minus our beta is pi over 3. That's our single function, or we can also combine the angle and say tan 2 pi over 3. Then to evaluate, very straightforward, let's sketch 2 pi over 3 in quadrant 2. Reference angle of pi over 3, so this is root 3, negative 1, and root 2. And then we evaluate tangent, which will be root 3 over negative 1, or just negative root 3. So we go from having a very complicated statement, where if we come back to this original statement, yes, we could have calculated all of those pieces separately and simplified, but applying the identity allows us to rewrite as a single function, which is a little bit faster to find the exact value. All right, that's it for now.